So, very good evening to all the participants, and welcome back to the third session of the day. And we have uh, the speaker for the session, and allow me to introduce him. So, we are having uh, Professor Y.P. Obulesu. He is a professor in the School of Electrical Engineering at VIT Vellore. He joined VIT University in May 2017. Previously, he worked in various academic organizations and industry from 1998 to 2017. He has received research grants from AICTE, UGC, and DST. He is also serving a reviewer for International Journal of Electrical Power Component Systems, Taylor and Francis, UK, IEEE Transactions on Power Electronics, IEEE Transactions on Industrial Electronics, International Journal of Energy Storage. He also served as a boards of advisory committee as a board of study member for electrical engineering department, JNTU College of Engineering, Kakinanda, Andhra Pradesh, and Sri Vasai Engineering College, uh, Andhra Pradesh as well. His current research interests include control strategies of electrical drives for electrical vehicle application, battery power management of electrical vehicles, solar power multi-source plug-in electric vehicles, IoT and machine learning applications to electric vehicles, soft switching and bidirectional DC to DC converters, DC microgrids for smart homes, and power converters for LED lighting system. He has also guided 10 PhD. He has also supervised 10 PhD scholars under his guidance. With this introduction, I will now hand over to the session to our esteemed speaker. Sir, please.
Good evening to you all. I thought my voice is okay.
Yes, yes, sir. It's okay, sir.
Okay. My PPT is visible to you.
Yes, yes, sir.
Okay. So I would like to discuss for next 1 hour on this active power filters for industrial motor drive. So actually, it is a case study. We have done this study a few years back at one of the cement power plant. So this is for cement plant. So I will show you briefly the functioning of the cement plant. Okay, so for 1 or 2 minutes, I will tell you how the cement plant will work. So then, what are the various electrical motor drives in the cement plant? Okay, so it is uh, this is the presentation what I would like to cover for today. So in this cement plant, okay, so with the existing, what is the energy consumption? So with the proposed thing, what is the energy saving? So those things I'll be discussing. So then industrial motor drives and also the amount of harmonics generated by those motor drives at the cement power plant. Then how to minimize those harmonics will be with active power filters. Okay, so then finally we will see. Okay, so how much harmonic has been reduced, etc. Okay. So now, main my objective here is that how this harmonics are even without power electronics, how the energy, electrical energy, so is being wasted with the help of power electronics converters or with power electronics circuits, how the energy can be saved. At the same time, this power electronics circuits and as well as the power electronic devices, how they will, okay. So on the other hand, how they will introduce the kind of harmonics. Those things we'll be discussing in this entire presentation. So if you take the cement plant, okay, so these are the main four basic processes which takes place in the cement plant. The first one is crushing. That means the raw material will be taken. So that raw material is of okay, so large size. So they need to be crushed into smaller particles. That can be done at the crushing plant and grinding plant. So then it will be taken to the next stage, that is a blending. Okay, so in this blending, there they will add the different chemicals in the appropriate proportion. So after adding those chemicals in the appropriate proportion, then it will be burned at the kiln by mixing all these chemicals. So then after that, okay, so it will be converted into fine powder. So at the grinding and clinkering stage, then it will be shipped to the transportation stage, that is handling stage. Normally these are the main four stages in the cement plant. Okay, so I have done this case study for Anjani Cement Limited. This is Anjani Portland Cement Limited. Few years back, it is located in Telangana. So now this Anjani Portland Cement plant taken over by Chettinadu Cement. Now it is no more Anjani Portland Cement Limited. Now it is a Chettinadu Cement Limited. Okay, so there we spent some time, maybe around 1 week or so. We spent there. We were there along with the suitable equipment. Then we carried out first energy, electrical energy auditing. So then we found that at certain places energy consumption is more. So then we have submitted a report to them. Then they asked with simple, with low cost, what are the best ways. So then we have suggested that case study I'll be discussing with you today now. Okay, so at the crushing plant, as I already told you, in cement power plant, mainly are the crushers. Okay, there at this Anjani Portland Cement Limited, two crushing plants are there. So we have taken one crushing plant for study. So then there they used three-phase slip ring induction motor. As we all know that if you wanted to have the high starting torque, so squirrel cage induction motor is not suitable. So quite naturally we need to go for three-phase slip ring induction motor. So to increase the starting torque, if you insert the external resistance into the rotor circuit, so we can increase. I thought if you recollect the torque speed characteristics of the three-phase induction motor. Okay, so if I take, so this is the torque, so this is the speed, torque speed characteristics of the slip induction motors like this. Okay, so now this is the starting torque, TST. Okay, at the crushing plant, normally we need more starting torque. So that's why we wanted to increase the starting torque, something like this. Okay, so to increase the starting torque, the conventional way was because this Anjani Portland cement was 35 years old. This is a 35 years old plant. So at that, because we have carried out this study for the existing cement plant. Okay, so now there they used, okay, this slip ring induction motor by inserting this external resistance into the rotor circuit. Okay, so with the help of the brushes and slip rings. So to increase the starting torque, to crush the, okay, so raw material into that required levels. Okay, so now for this motor, we have done the calculations, how much they are paying every month. That also we have taken into consideration. Then we have calculated. Uh, we have presented this report to them. So the external resistance which is inserted into the rotor circuit for that one of the crusher plant is 4.7 ohms. So the rating of that slip ring induction motor, it was 110 kilowatt. So current is 138 amperes. So this is the voltage rating. So then we have calculated the power loss by taking this I square R. So then it is coming around 89.5 kilowatts. Okay, so then per day we calculated, then it is coming around 2148 kilowatt hours if you take in terms of the energy from this power loss. So then per month it is coming around 64,444.8 kilowatt hours. Then annual consumption is 7,73,337. So we have taken the electrical tariff because, as I already told you, that we have carried out this study a few years back. At that time, okay, so industrial tariff is concerned for those regions. So it was around 6 rupees. So I have taken 6 rupees. Then we have calculated. So that means the electrical tariff per year is 46 lakhs 40,025 rupees. Okay, that means it's not a small amount, it's a huge amount. Because when I was working a few years back in one of the organization, so that education institute is also having that cement plant. So that's why they asked us to go and carry out this energy audit. So then we have done this electrical energy audit there. So we came to know that at that time. So the at the crushing plant itself, okay, so the electrical energy consumed is too high. So for that, by taking this electrical tariff, the annual electrical tariff is coming around 46 lakh. So it is a huge amount. They wanted to reduce this. So then we suggested different methods. Okay, so as we know, we have not suggested any. Okay, so for crushing plant, any advanced technique because there was a cost constraint. So they asked us to be replaced by this existing one by a new one, not motor, by the new control strategy. So with the 10% cost, okay, around the 10% cost, they don't want to invest more than that. So then we suggested slip power recovery schemes and also field oriented control strategies, etc. They're not because of the cost involved and also complex. So because they're only diploma holders who are there, so they don't know about all the things. So they wanted to have the simple control with the reduction in the electrical energy consumption, and they wanted to save this electrical bill. So then we suggested this simple one. This is the static rotor resistance scheme for that crusher plant slip ring induction motor. So if we all know, this is a very basic circuit. So instead of keeping the fixed external resistors in the rotor circuit, so by replacing that, okay, so we can insert this. Okay, so this is the diode bridge rectifier circuit. This is the, okay, chopper or simply a power electronic switch. Okay, so this is the one resistors. Okay, so now here we all know that majority of the electrical engineers, they might have studied this about this. It's not great thing, but the thing is that once you take a particular okay, so case study particular plant there, if you apply this, then we'll know surprisingly that how much energy that can be saved. So these ratings of this IGBT switches as well as this direct pairs are concerned. So at that time we suggested 150 kilowatt. Okay, so this rectifier as well as okay, so this IGBT switch of 2 kilohertz. So now with this we have calculated, okay, so what is the energy consumption. So as we know that this effective resistance, so between these two terminals, okay, so if you take this is the A, this is the B, between these two terminals, if you take the effective resistance, so this is the formula, so which is a very standard formula, everybody knows it. Okay, so now by taking this duty cycle of the switch which is connected across the resistor at zero point 0.8, so then by calculating the effective resistance across the terminals A and B, okay, so then based on that, okay, we have calculated the so energy per day, similarly annual energy. So it is coming around 1,56,804 kilowatt hours. So then based on this electrical tariff of the 6 rupees, then we calculated it's coming around 9,40,000. So earlier it was with the conventional rotor resistance, okay, so it is 46 lakhs 40,000 25. So with this static rotor resistance, it is coming around 9 lakh 40,000, okay, 824. So then if you see this, this is the saving. So that is 36,000 999 9,000 99,201, means approximately 37 lakhs. So so we suggested over a period of time they replaced that conventional rotor resistance by this static rotor resistance. They have seen that there is a huge amount of energy saving. Then later they wanted to replace all the conventional speed control strategies by new and also advanced speed control strategies. So later on, stage by stage, they replaced. Why I have given this very simple and particular case study means this is actually done. So through this we'll come to know that even though, okay, so you have taken a very simple thing which is known to us very well. So with the help of our power electronics we can save a lot of energy. So here that one rectifier circuit, one switch that we are calling it as a static rotor resistance control for slip ring induction motor. By adapting that there, so we're able to save this much, 37 lakhs per annum. So then they realized that they wanted to replace the old ones by these new ones. Then once they started replacing these old control strategies by new control strategies, so then they started coming across new problems. So those problems we will see how to address them. Okay, so by replacing this conventional things by seeing that advantage by this power electronic converters or power electronic circuits, so they started facing this power quality issues. Maybe you might have seen this power quality issues. So this is nothing but the manifestation of this voltage and frequencies. Normally, when you take any AC motor drives or anything, so AC voltage means by default we will take the sinusoidal voltages. So as far as the nominal frequency of that sinusoidal voltage is concerned, so we will take either 50 Hz or 60 Hz. As long as we are in the Asian countries, by default it should be the 50 Hz. In Europe and USA, it might have been 60 Hz. So that means any deviation in the nominal values of this voltage and frequency can be treated as a power quality issue. So even though we are calling it as a power quality issues, majorly the kind of quality is the voltage quality. Why? Because the load which is connected to the power supply, so is not in our hand. So that load, okay, so that means the current drawn by the load, so entirely depends on the nature of the load. Okay, so now there might have, you might have seen different sources of the power quality issues. So here I'll be taking only the adjustable speed drives, variable speed drives, because they are the ones used in this cement plant. So this speed adjustable speed drives or variable speed drives. So these are the non-linear loads. Okay, so this variable speed drive is concerned. If I put it in the simple words, okay, so there is a motor. So I might have seen that there is a one power converter. This may be AC to AC converter or AC to DC or DC to AC, anything. So it is a power converter. Okay, so then here it is a source. Okay, so that means this source may be either AC source or DC source. Okay, so that means so this is the case. This put together, so we can call it as variable speed drives or maybe adjustable speed drives. Adjustable speed drives. Of course, there will be a load on this motors. Okay, so if we take this is the AC motor, quite naturally, this is the DC to AC converter. Okay, so if it is a DC to AC converter, so then available voltage is the AC voltage. So that's why we have to use here in between. Okay, so one rectifier. This rectifier will convert this AC to DC. Okay, so then this DC will be converted back to AC. But the thing is that we are able to control the this AC inverter AC voltage as well as its frequency such a way that we are able to control this motor speed effectively. Sometimes based on the motor control strategies, we are able to control its speed torque independently. Like if you apply the field oriented control or direct torque control, etc., etc. So now my focus is not to discuss about all the speed control strategies of these motors. If these motors are operating with a particular speed control strategy, what is its impact on this source? Okay, so that we would like to see. So when we treat this adjustable speed drive, which is having the motor plus this power converter as main components, so how this operation of the motor impact the, okay, so power supply. Okay, so that utility power supply is connected. Okay, when it is connected to this drive, okay, so it will also impact the other loads which are connected to the same supply. So there, okay, so we'll come across that means when this motor is drawing the, okay, so load current, so because of its operation or due to its operation or because of its operation, so at the supply side, okay, so where more than one load is connected, so other than our adjustable speed drives, another loads are connected where, so this harmonics are injected into the supply system. So to eliminate those harmonics, okay, so what are the remedies which are available that we'll be discussing? As I made a mention very beginning that so that the cement plant, Anjani Portland cement plant, conventional drives were replaced by power electronics drive. power electronic controlled drives. These power electronic controlled drives, okay, so they are introducing the harmonics. That means they would like to save the energy. So in the process of that, okay, they replace this power electronic controlled drives. Now this power electronic controlled drives, now they are injecting the harmonics into the supply system. Again, they are facing a new conduct problem. Again, they approached us. We went there. We spent some time. So we suggested, okay, some of them. So just for basics, okay, so let me take what is the harmonics. So as we all know that it's nothing but the integral multiples of the nominal frequency. If the nominal frequency is say 50 hertz, any multiples of that 50 hertz, okay, some of these multiples of this 50 hertz, so is nothing but the harmonics. So now if you see this here at the rectifier side, okay, so as I already told you that so AC will be converted to DC. Again, the DC is converted back to AC. Okay, so at this rectifier side, that is the front end converter side, so the current drawn is not a sinusoidal. That source side current drawn is not a sinusoidal, it is a non-sinusoidal. Okay, so if you resolve this non-sinusoidal current into different components, we'll come to know that okay, so there are multiple integer components, frequency components of the nominal frequency. Here just for illustration it is given. So that means so by applying any Fourier series etc, we can analyze what is the third harmonic component, what is the magnitude of the fifth harmonic component, what is the magnitude of the seventh harmonic component, etc, etc. Okay, so now to generalize this, okay, so this nonlinear load, in our case, variable speed drive. So this variable speed drive or adjustable speed drive. So these are the nonlinear loads. They are drawing the non-sinusoidal current from this source. When they are drawing the non-sinusoidal current from this source, at the point of common coupling, as I told you that, okay, so if I take this is the source, okay, let me take another color, maybe red color. Okay, so if I take this is the source, okay, so this is the point of common coupling, that is a PCC, where more than one load is connected. Okay, so like this, so many loads are connected. So our adjustable speed drive is one of the load which is connected at this PCC. So now this adjustable speed drive, which is inducting the harmonics, okay, at the PCC, that means at this supply. So other loads which are connected to the same supply also getting affected. Okay, so now these problem need to be eliminated. Okay, so to know how much distortion, okay, which is present at the supply side, both in the voltage as well as in the current. Okay, if you take the voltage, okay, so voltage distortion. If you take the current, then current distortion. To determine how much distortion which is present there, we can use one of the parameters. This is the parameter, total harmonic distortion. Okay, so there are power quality analyzers. So with the help of them, we are able to find out what is the THD. Okay, so at that particular terminal of the adjustable speed drive, both voltage THD as well as the current THD. So earlier total harmonic distortion, this is the term which was used to measure the distortion in the voltage and current. Later on, to differentiate the distortion in the voltage and current, for current, okay, people started using this total demand distortion. So okay, so this is just to differentiate the distortion in the current. Okay, so earlier THD was used for both. So now THD for the voltage. Okay, so for the current TDD. Okay. Now, so after studying and also nowadays everywhere there is a electronics. Okay, at the power level there is a power electronic. Without power electronics, nothing is there. So whether you take a microgrid, you take the electric vehicle, you take the okay, so cement plant, whether you take the paper mill or whatever you take. So everywhere, okay, so there is a power electronics. Without power electronics, there is nothing. So at the same time, this power electronics is okay. So introducing the harmonics. So that's why just like air pollution, there is a kind of harmonic pollution. So this harmonic pollution need to be okay. So minimized. This harmonic, there are certain standards. Okay, so these are the harmonic standards. So they will provide the basic information about what is the allowable. Okay, so harmonic content THD. Okay, so for the current as well as for the voltage, so for the given load, we cannot generalize that. Sometimes we say that 5% THD is allowed. No. So what is the load? Okay, so what kind of load we wanted to use? Okay, so is it for voltage or current? Okay, so let us suppose you take the sensitive loads, so more accuracy is required. You take some other load like agriculture pump application, there that much precision is not required. If that is the case, then you don't have to limit the THD. Okay, so in the voltage to 5%, where you can allow even up to 7% also. So that's why even you take the current also. Okay, so depends on the load. Okay, so depends on the nature of the load, so nature of the load and also the application. So based on this, we'll decide what is the allowable THD. So this IEEE 519 will tell that what is the allowable THD. So these are the other standard IEC 610047, IEC 61004. This will give the basic information about the, okay, so harmonics. There here this harmonics can also be divided into, okay, so into different types. Another category of the harmonics is this interharmonics. Okay, so as I made a mention just now that so multiples of nominal frequency. So that means if I take n into frequency say 50 Hz, okay, so where this n is equal to, this is the harmonic where this n is equal to, so it may be, okay, so 2, 3, 4, 5, etc., etc. Okay, let us suppose if this n is not integer, okay, so it may be 1.5. Okay, so then this 1.5 into 50, so will also be considered the harmonic component, but that is the interharmonic components. Okay, so of course, here in this study, we have not considered this interharmonics. We have considered, okay, so this so only integer harmonic components. Okay, so not interharmonic components. So now uh, we came to know, maybe after some time I will show you the amount of THD present at the different electrical motor drives in the cement plant. Okay, so to minimize that, we can go either passive filtering or active filtering technique. But the thing is that okay, so whatever the filtering use, ultimate objective is same, to reduce the harmonics or to minimize the harmonics, but okay, so in the voltage as well as the current. At the same time, once you reduce the THD, total harmonic distortion, quite naturally the phase angle between the, okay, so supply voltage as well as the supply current improves. Okay, that means reduces. So once the phase angle reduces, quite naturally power factor improves. Because in industry in India, I thought you might all know that. So power factor must be maintained at 0.95. Whatever the load it is, whatever the load it is, power factor must be maintained 0.95. So all the industries they are supposed to maintain this. If no industry is maintained this, quite naturally there will be a penalty. Okay, so to overcome to avoid from that penalty, so almost all the industries they will maintain this 0.95 power factor. So this power factor will get affected if the harmonic distortion is more. Okay, so now we can go for either passive filtering or active filtering, but passive filtering is very simple. Okay, so simply, so we have to use the LNC. You can connect either in series or parallel combination such a way that we can eliminate or we can minimize one harmonics. Let us suppose four harmonics are there, then we need to have the four LC component. That means it's a complex, and also due to one reason or other reason. So if the current etc changes, then we need to change the design of this. Okay, so that's why, as far as the advantages are concerned, it is very easy, very simple, okay, low cost etc, but the disadvantages are concerned, okay, so as the load current etc changes magnitude, quite naturally, okay, so we have to change the values of this. And also, okay, so the biggest disadvantage is that at certain frequencies this LNC component may create the resonance. So these are all the disadvantages, and also these are the passive components. Okay, if any modification is required, we need to replace them. It's again a headache. So that's why, so the best one is this active filtering. So this active filtering, okay, so is very effective in minimizing the harmonic components, and also we can eliminate any number of harmonic components. Okay, so and also we can compensate the reactive power also. So that means, so we can minimize the harmonics, at the same time we can compensate the reactive power, so that we can improve the power factor. So these are the these functions we can achieve simultaneously by adopting the suitable control strategy. So if you take the simple okay, so this diagram, it is very simple to understand this active power filter. Okay, so if you consider this is a simple block diagram only. So if you take this is the non-linear load. So in our case, this is our variable speed drive or maybe adjustable speed drive. Okay, so now, so this adjustable speed drive is driving the non-sinusoidal current. It may have, okay, so maybe third harmonic, fifth harmonic, seventh or ninth, or maybe any number, maybe up to 30 or up to 40, any. Okay, so now when we wanted to minimize these harmonics other than this fundamental, okay, so we have to design a filter in this active power filter. So this all comes under active power filter. So this active power filter, okay, so is again a power electronic circuit, as I already told you that. So to control the speed of this motor, we are using one power converter or power electronic converter. So this power converter function is to control the speed and torque of this motor. Okay, so this may be a power source. Okay, so now here this motor is drawing the non-sinusoidal current. Okay, so that's why it is introducing the harmonic into the supply system. So to eliminate or to minimize that, we are using another power converter, okay, which we are making it to act as a active power filter. So this power converter will act as a active power filter. So that means, so whatever the power electronic circuit which is responsible to introduce the harmonics into the supply system, to compensate them, we are using the another power electronic circuit. Okay, so this another power electronic circuit, so we are making it to act as a active power filter. This active power filter is able to minimize this. Okay, so that means this one is producing the harmonic components. Okay, so these harmonic components are out of phase, 180-degree phase shift with respect to its original, okay, so load current harmonics. So by adding these two, so we are able to compensate the load current harmonic component. So at the source side, okay, so only fundamental component will present. Okay, so that means here load, okay, so as far as the load is concerned, earlier it was driving the non-sinusoidal current. Now also it is driving the non-sinusoidal current, which is having harmonics. Okay, so what we are doing is that at the supply side, at the source side, okay, so by connecting this active power filter at the supply side, we are improving the quality, okay, both in the voltage as well as the current, so that the phase angle between the voltage, supply voltage and supply current can be, okay, so improved. That means reduce, so that we can improve the power factor. So that means we have not done anything for the load. So earlier, now also load is doing its own function. It is doing its own nonlinear current, that is a non-sinusoidal current. By adding this at the supply side, we are improving the quality, both voltage as well as the current. Okay, so now here this is a simple diagram. Sometimes this is the load which is represented with okay, so diode symbol. It doesn't mean that diode. So any nonlinear load. So now, by looking at this here, so this load is having the harmonic components. Okay, so active component as well as reactive component. That means you take the current, this load current into active component plus reactive component. Okay, so sometimes there may be a okay asymmetrical waveform. Positive portion may not be equal to the negative portion. Of course, in our study, in this case, we have not considered this. That can also be done with this act. So that means this active power filter is able to take care of the, okay, so harmonic current, reactive current, as well as if there is any unsymmetrical unsymmetric current is there, that can also be done. So that means at the source side, so this source is able to supply only the active component of the load current. So this entire things, okay, for this load, so these are locally, okay, so by connecting this active power filter, so we are meeting the load demand locally. Okay, so okay, so that's why this source is relieved. Okay, so from this reactive component of the current, harmonic component of the current, etc. That's why, so its power factor improves. This is one of the reason why the power factor improves. Okay, so now this active power filters are normally three types: shunt active power filter, series active power filter, and hybrid power filter. So that means combination of the hybrid in the sense, okay, so here a combination of the shunt and series. Okay, so sometimes that can also be called as a okay, so because sometimes people hybrid means they may think that okay, so active filter plus uh, active power filter plus passive filter, this can also be used. So many researchers, they have done this okay, so hybrid research on this hybrid filters. But here okay, so shunt filter, shunt power filter, series okay, so active power filter, so as well as the sum of these two. Okay, I'll be discussing here shunt active power filter. So that means if you take this, this is the shunt active power filter. So if you take this shunt active power filter, okay, so here this power filter, this harmonic power filter or active power filter is connected in parallel to the load. It is connected in shunt to this. That's why we are calling it as a shunt active power filter. Mainly, this shunt active power filter is to eliminate the harmonics in the currents. Okay, so now if you connect this active power filter in series to the load with the help of the transformer like this, then this is a series active power filter. Okay, so this series active power filter is to minimize the harmonics in the voltage. Okay, so if you wanted to eliminate both, yes, we can connect a combination of these two. Okay, so this already I told you this active power filter. So locally meet the demands of the load, demands of the non-linear load, so that the source will supply only the active component of the current, load current. Okay, so this is the detailed block diagram. This is the detailed block diagram of the shunt active power filter for non-linear loads. Okay, so this is the three-phase AC supply. Okay, so this is the non-linear load, adjustable speed drive, okay, which is connected to this supply here. For simplicity, okay, we have not shown all the things, so we have considered this entire thing. So as I already told you, so it is a rectifier, this is the inverter, this is the rectifier, this is the inverter, okay, this is the AC motor. Okay, so now our objective is not to discuss about the things. Okay, so these are taking the non-linear loads, non-linear current. Okay, so from the source. Okay, now this things, entire things comes under active power filter. Here it is shunt active power filter. Okay, so if you take this shunt active power filter, shunt active power filter. Okay, so now there are different control strategies are available for this shunt active power filter. So mainly two control strategies. Okay, so one is the power component method. Okay, so another one is a current component method. That means PQ method. So this is a current component method, IDIQ. Okay, so here we have considered the current component method to control the shunt active power filter. As I already told you that shunt active power filter is nothing but the power electronic converter. Okay, so here we use the two level converter, which is nothing but the same. So if you take this here, this is the okay, so inverter here, it is acting as a shunt active power filter. Okay, so same three leg two level inverter. So this is the DC voltage here. Okay, so if you use the capacitor to provide the DC supply to this, it is converting this DC into AC. So that is being injected into this supply system. It's nothing but whether you can take it as a filter current or maybe the compensating current. So compensating current. So this is the source current. So this is the load current. Okay. So then the source current is equal to load current plus compen load current plus compensating current. This compensating current is okay, compensating the harmonics. That means here first we need to sense the okay actual current. Okay, so here this is the sensing the actual current. Okay, so this is the actual current. So this actual current, because in order to implement this either PQ method, that is a power component method, or current component method. Okay, so we have to take okay, so currents, actual currents, IA, IB, IC, or maybe I1, I2, I3. Okay, in this case I have taken I1, I2, I3. Okay, three phase currents, they are converted into an equivalent okay, so ID, IQ, this is the IQ, this is the ID. So then after, this is the filter, this is the low pass filter. Okay, so to filter out any of the okay, so noise signals from this current component, then they will be compared with okay, so reference currents, so ID star as well as the IQ star. So these reference currents are generated. There are set of mathematical equations are there, so I have not kept all those mathematical equations because my intention is not to go in depth about this active power filter. My intention is how this active power filters can improve the okay, so total harmonic how they can minimize the total harmonics for the industrial motor drives. Okay, so uh, uh, okay, so by taking this reference currents, by comparing that with the actual currents, so then so here this DC link voltage compensation can also be done, because here capacitor is being used. So this capacitor voltage is not constant, is not maintained constant. So if there is any deviation, so that can be okay, so compensated okay, so with this. Okay, so for this we can use this. So now uh, let me explain you this principle of this shunt active power filter. Okay, so to minimize this harmonics. Okay, so now this is the simple whatever the as I already told you that here we have considered the two level inverter. So three leg two level inverter. Okay, so let me take one of the legs. Okay, so one of the legs. So each leg is having two switches. Each leg is having two switches. You take, this is the load, this is the source. Now if you connect this here, so our shunt active power filter, so this is the interfacing inductor. Okay, so if you take this interfacing inductor here, now how this particular one of the legs switches can be controlled to control the current which is injecting. If you take, this is the case, it can also be considered like this. This is the compensating current. Okay, now if the switch is okay, so kept to here, we are able to control the voltage at this. Okay, so then, so this is the capacitor voltage. So similarly, if you keep this okay, so we are able to control the voltage at this. Okay, so that means either wanted to add the voltage or whether wanted to reduce the voltage at this okay tip or at the terminal of this, by okay changing the position of this switch, we are able to do that. So if there is any difficulty in understanding this, maybe in the next slide we can understand it very easily. Okay, so now this is the okay two level three leg inverter. Okay, so now this what I explained you. So you take, this is the voltage. Okay, okay, so you take maybe this is the B, or maybe here we have taken ABC. Let me take, say this is the 2, this is the 1. Okay, so voltage at this okay can be controlled. Okay, so by turning the switch at this position or by turning the switch at this position. Same thing for the phase B as well as the phase C. Okay, so by connecting this capacitor voltage which appears across this. So through this phasor diagram, let me explain you this very clearly. So the principle of controlling this shunt active power filter, as I already told you that the shunt active power filter main function is, okay, so to minimize the current harmonics. That means we are injecting the compensating current. That compensating current is also having the harmonic, but 180-degree out of phase with respect to its actual load current harmonic components. Okay, so here to control this current, okay, so here we are controlling the voltage at this. So that means this one. If you take this voltage, say VB, okay, so okay, this voltage is say for example VA. So we wanted to control the voltage at this by controlling the switching positions. Okay, accordingly, so this voltage is to be added or maybe subtracted. That means through this phasor diagram, we can understand very clearly. So this is the voltage at the A terminal. This is the voltage at the B terminal. That means by controlling this voltage at the B terminal, we are able to control the magnitude as well as the, okay, phase angle of this current. So that is the basic principle which is involved in this shunt active power filters. So now if you write down the mathematical equations for this, okay, so you take the particular thing. So if you take this voltage is a VB1, so then this is having okay, so this whatever the line which we connected, okay, so that line may be having the resistance and inductances. So we can write down the equations for the phase 1 like this. Similarly for phase 2, phase 3, okay, etc., or VA, VB, VC. Okay, so now as we have seen the main block diagram there, we are supposed to convert this ABC into, okay, so that means three phase component into an equivalent two phase components. So again this is okay for converting back to the original component. So again to convert this into the synchronously rotating reference frame, where we'll be having the, okay, IQ as a DC component. Okay, so that we'll have the effective decoupling between the D axis circuit as well as the Q axis circuits. These are all the equations very well known to everybody. So now you take those equations, and if you keep them in state space form, okay, so here what are the equations you have seen here, these equations. Okay, so now these equations, if you keep them in the state space form, okay, so then we'll obtain this one. And also for easy understanding, so you take this entire thing is some UD for D axis, similarly UQ for Q axis. Okay, so that means this is only for our easy understanding. Okay, so now we have kept this D axis as well as the Q axis voltage equations in state space form. So then if you put it this way, so then simply this is the input, okay, this is the current. So that means okay, this ID IQ currents we are able to get it. So these currents can be compared with this reference currents. So ID IQ reference currents. Okay, so then for DC voltage compensation, if you take the DC link capacitor, so the DC link compensation can also be done by adopting one PI controller. Okay, by comparing the actual DC link voltage with the reference DC link voltage. So that because this compensating currents also depends on this DC link voltage. If there is a variation in the DC link voltage, that variation will affect the, okay, compensating current effectiveness. So that's why that can be. So this is the phase log loop. Everybody knows this because to take the transformation from alpha beta to DQ, that means stationary reference frame to. So here, so we need this theta or omega t. So to obtain that, we use this phase log loops. So simply, okay, by taking all these things, these are the main things. Okay, these are the inputs. So these are the outputs for the controller. Okay, so then by implementing this, okay, so for shunt active power filter, again after taking back to this original variables, okay, so on the generating the PWM technique. Okay, so here in this case we used here, okay, so for this uh, any PWM technique can be used here, but here we use the space vector modulation at that time. Okay, so this is same block diagram earlier, whatever the block diagram I have shown you. So now I explained you the principle of the shunt active power filter. Very beginning I told you. Okay, so the simple operation of the cement plant. Now this is the layout of the Anjani Portland cement plant. So there are different okay, so sections. Okay, there are different motor drives are there at each motor drive. Okay, so we have done this harmonic analysis. Okay, so we have taken this as far as the plant details are concerned. At that time, they used to produce 2,500 tons per day. Okay, and also majority of the okay, so electrical motor drives used to consume more power, so that's why. So they wanted to reduce that, so they replace the conventional drives by okay power electron controlled drives. So we have to do this harmonic analysis, we have taken the Fluke 434 power quality analyzers. Okay, so continuously we have connected because we wanted to see the variation in the data. So continuously we have connected this for 2 days. We have taken the data for both voltages as well as the current. I thought those we are having some experience on this Fluke 434 power quality analyzer, so they will come to know that this Fluke okay, so also comes with the software. So whatever the data we have taken with this okay, so instrument, that data can be transferred to our okay laptop. So there we can use this okay, so all this harmonic profile. So that what we have taken here. So yeah, so this is the at 132 kilowatt cooler ID fan. So this is the voltage as well as the current harmonic profile. So voltage THD is 2.8. Okay, so current THD is 9.1. So they are not so high. Similarly, at 650 kilowatt fan also, so we have taken the also okay voltage THD is not so effective 1.6. Okay, current THD is 4. So they're also more or less within the limits. So here also the same. They are not anything any abnormal values. Okay, so like that we have taken the harmonic data. Okay, so at a different motor drives at the clinkering section also this is the data. Okay, so this is a cooler fan 1, cooler fan 2. Okay, so this is the current of the cooler fan 2. Okay, this is the cooler fan 4. So now after summarizing all these things, okay, at a different motor drives, okay, so the voltage THD as well as the current THD. So if you see this, more or less all of them are within that. But this cooler fan 2, okay, so their current THD is huge. That is a 60.4. Okay, so why the THD at the cooler fan 2 was too much? Okay, so means as I already told you, they at that time, so they replaced. Okay, so okay, conventional motor drives by power electronic drives stage by stage. Okay, so wherever they use the okay, so more power electronic converter circuits, there we noticed that okay, so current distortion is more. Okay, so we have taken that data. So because we are from academics, so that's why at that time we suggested, we carried out, we submitted the report on that. We suggested, and we have taken the data to our academic institution. So then we have done the simulation. Okay, study. That means in the MATLAB we have implemented this active power filter for the same cooler fan data. So then in the simulation, okay, so we found that. This harmonic okay, so is reduced. So with at the cooler fan 2 okay, so without active power filter, so 60.4, with the active power filter 3.38 only. This is done only in simulation because at that time we could not have enough facilities, okay, so to go for hardware implementation. So that's why, and also we could not afford the cost because okay, so of the high power rating. So that's it about. So regarding the finally conclusions are concerned, so we have done the harmonic analysis with the Fluke 434 power quality analyzer at Anjani Portland Cement Limited. So for different electrical motor drives, we found that at one of the motor drive, so which is having advanced power electric control, their harmonic current injection is more. And also, okay, so we suggested to go for active power filtering technique. So later on, okay, that company was taken over by this Chettinadu Cement Limited. So later on, we did not visit, so we don't know what happened there. So these are the references we have followed for this. So that's it about my presentation for today. If you have any questions or queries, you can. I thought I'm supposed to give the presentation up to 5:50, so remaining 10 minutes for questions.
Right, sir. Right, sir.
Am I
Right, sir.
right? Yeah.
Right, sir. So the session is now open for the discussion. If any participant wants to ask, they can ask or discuss anything.
So we carried out this work 6 years back. So
Great work, sir. Great work.
uh, around that time, okay, so commercially active power filters were not available. Not 6 years back, if I remember correctly, maybe 8 years or 9 years back. Okay, so this is around 2012 or 13, if I remember correctly. So around that time, and the plots dates were also there, and the harmonic profile plot dates are also there. Maybe if you look at this, we'll come to know when exactly we carried out this.
Okay, sir.
2009, 399. Okay, so that means almost 10 years back.
15 years back.
So now at that time,
At least you are
nobody.
having results as well. And we are. I'm not having the results of my PhD. Yeah, sorry, PhD.
Okay.
You-
Now majority of the companies now they develop the active power filters. Now commercially they're all available at even at Chennai, Bangalore, Hyderabad, Pune. So wherever you take majority of the okay, so industry commercial active power filters are available. So in 2009, uh, only one company was there at Mumbai. Okay, that company used to supply. So, yeah, any questions, anything, please?
Some sir, one participant has asked in chat box, any future scope regarding this work?
It's already so much work has been done. Now, future work is concerned. Okay, so I suggest you take this block diagram somewhere. This active power filter, this block diagram. Okay, so okay, this is a Simlink model. Okay, no problem. So here, as I already told you that this shunt active power filter is nothing but a power electronic inverter. Okay, so there we used IGBTs. Now, same IGBTs can be replaced by okay, so wide band gap devices like silicon carbide or maybe GaN devices. Okay, so you can try so that we can reduce the size, we can improve the efficiency. That can be done. I thought very okay. So few researchers done on this. As a future scope of research at present, because we are in 2023. Okay, so now we can consider wide band gap devices for shunt active power filters. You can try to implement it. Is it is it fine?
Yes, sir. Yes, sir. She has written. Thank you, sir.
Any more? Even at any education institutions here, because when I received a invitation from you, from the organizer, during that time I was out of station and also because of some other works. Okay, so I could not pay much attention. So that's why whatever the work which we have done, I thought of sharing that. Okay, so uh,
So very
we also done this for single phase loads for our computer labs, etc. In one of the when I was working in that institute before VIT, I was working in one of the organization. There we have done this. Okay, so harmonic analysis for computer centers. Okay, so they are all single phase loads. Okay, so there we install actual active power filter hardware implementation. The data was also available, but it was there somewhere, I could not get it. So, and also organizers given only 45 minutes time, that's why
Yes, sir.
I
Yes,
will
sir.
not.
So it was a really nice presentation. Any doubts from participants? Okay, sir. I think there is no more doubts. So
Okay.
we can stop here.
So then, thank you all. Thank you for your patient listening, and also I would like to thank the organizers for giving me this opportunity. So thank you all.
So can I share the screen for a second?
Sure, 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 please.
Sure, sure, sure.
You want me to stop the sharing, or
I have shared my screen, sir.
okay?
Okay, okay. My screen is visible, sir.
Yeah, visible, visible.
Okay, okay. So, sir, please accept this uh, a token of appreciation virtual as we are doing the virtual mode. So, please accept our from our end token of appreciation, sir.
Thank you, thank you.
Thank you, sir. Thank you, sir.
So, will you be providing any certificate for us?
Sure, sir. Sure, sure, sure. This is just sure, sir. Sure, sure, sure.
Thank you,
Thank you so much, sir. Thank you so much.
thank you, thank you.
Okay,
Thank you,
participants.
sir.
Yeah. So we will meet tomorrow at the 10:50.